Okay, so I'm going to run through the homework problems from homework 7 and kind of give you a synopsis. I might not go into a lot of detail, but at least kind of tell you the idea. Okay, so a person who claims to be a psychic says the probability P that he can correctly predict the outcome of the value of a card drawn from a deck of cards in another room is 1 in 13. The value that applies with random guessing. Okay. He says it's greater than 1 over 13. So this is what he's claiming. If we want to test this claim, we could use the data from an experiment, okay, in which we do n card draws, okay, and run a hypothesis test. Okay, so first of all, when you want to rule out certain things, the null hypothesis always has the equal sign. So we know that automatically it's not A, it's not B, and it's not D. We want to test the psychic's claim. So if we're testing something, we're trying to prove it, right? So what we're trying to prove is we're trying to prove that the percentage of times he guesses correctly is greater than 1 over 13. Okay? So here we're testing F. Okay. Now you have to be careful because in the notes I say when you're testing a manufacturer's claim, you're going against the claim. But here, this is more like a research project, right? We want to prove something. We want to prove that he really is psychic. And so what we're trying to show, which is the alternative, is that the probability is greater than 1 over 13. Okay. So we have a hypothesis test where the null is that the population proportion is 50%. And here the sample percentage is 0.37, and we got that from a sample size of 100. So first of all, we have to think about the test statistic, okay? And I didn't dwell on this a lot, but the test statistic is basically the z-score for the sample percentage in a population where the population percentage is the value under the null hypothesis. So let me kind of do it like this. Okay. So what we're thinking of is this. We're thinking that under the null hypothesis, we're saying that the population percentage is 50%. Okay. And what I get from the sample, this is my hypothesis, from the sample, I get a sample percentage of 37% using a sample size of 100. And I want to know what is the test statistic. In other words, this is the value that I'm using to test the null hypothesis with. I mean, I'm testing the null hypothesis with. So we can do this in StatCrunch, okay? You can do this by hand, but you can also do this in StatCrunch. So the way that we do it in StatCrunch is we run the hypothesis test. So I'm going to go here and stat. Okay. And I'm doing z-stats, one sample with summary. Hold on, sorry. I'm doing proportion stats, sorry. Proportion stats, one sample with summary. Okay? So the number of successes, if I look at this, I have to go back and read the problem, right? It's 37, the sample proportion is 37%, sample size of 100, so this is the number of successes, right? Sample proportion is always of successes. So I had 37 successes, okay? A sample size of 100, number of observations. I'm testing to see if it's the null hypothesis is that it's equal. Let me go back and read the problem here carefully. So the test statistic will actually be the same no matter what sort of hypothesis test you're running. So I can just run it with whatever I want here. It doesn't really matter what the alternative is, okay? And this is my test statistic. Z-stat. Okay. And what this is, and it's minus 2.6. Okay, that's my test statistic right here. And let me explain to you what this is. Okay, this is going to be whoops, I don't know why I didn't copy and paste. Okay, that's my test statistic. And here's what this is, okay? So this is saying if the null was true, then we know that sample percentages come from a distribution. Excuse me, my pen just went out there for some reason. Okay. So what we know here is we know that sample percentages would come from a distribution where the mean was 0.5 and the standard deviation was 0.5 divided by the square root of n, which is going to be 0.05. Okay? And now we would compute the z-score for this value right here. So the z-score would be equal to p minus pi under the null hypothesis divided by the standard deviation, which is pi naught times 1 minus pi naught divided by n square root of. Okay. So this ends up being 0.37 minus 0.5 divided by 0.05. And when all the smoke clears, okay, here I'm going to get 0.13, and when I multiply that by 20, which is what the division by 0.05 is, right? I'm going to end up getting minus 0.13 divided by 0.05, and this is where my minus 2.6 is coming from. Again, remember the test statistic is the z-score for the observed sample percentage in the distribution of sample percentages I would get if the null hypothesis was true. So that's a lot to think about. So now what is the p-value? So now they give you the alternative. So now I can go back and rerun the test. Okay, so I'm going to go back and run it. The alternative was that it's greater than. Okay. Hold on. Is it greater than? Hold on. No, less than. I was going to say it didn't make sense to be greater than. That'd be a dumb test. The alternative is less than, and you compute it, and that's your p-value right there. Okay? So I'll go back and paste that. And you got to watch with the rounding number of decimal places, so it's easy to get that wrong. Okay. And so it's asking you whether or not the p-value is giving you evidence against the null, and the answer is yes. Okay, small p-values means it's very unlikely the null is true, so that's strong evidence against the null. So we automatically know it has to be A or B. And strong evidence against the null means the p-value indicates the null hypothesis is not plausible. Okay? And there we go. What's going to give students trouble is the test statistic. Just tell them to run it in StatCrunch and don't worry about the alternative. The test statistic is the same no matter what the alternative is, okay? Because again, you're looking at the estimator in the null distribution. So we don't care about the alternative to get the z-stat or the test statistic here. Okay. All right. A certain drug is used to treat asthma. In a clinical trial of the drug, 17 of 295 treated subjects experienced headaches. And then it shows you some output from the test of a claim that less than 10% of the treated subjects experience headache. Don't worry about the last line. Use the normal distribution as an approximate to the binomial distribution. Don't worry about that. And our alpha is 1%. So first of all, if we think about it, we're testing the left tail. We're testing to see if it's less than, okay? So the alternative, the thing that we're trying to prove, is we're trying to prove that it's less than 0.1. And you can see that right here, the very second line here, right? And so we're testing the lower tail. What is the p-value? You can pick that right off. Okay, so it's 0.0076. Okay. Again, the p-value is relative to alpha, so the p-value is less than alpha, so we would reject the null. Again, the null is always has the equal sign. Okay, so the null is always at its 0.1. We're going to reject the null because the p-value is less than alpha. So your final conclusion is that there is sufficient evidence to support the claim that less than 10% of the treated subjects experienced headaches. So that would be B. Okay. We would reject the null because the p-value is less than 0.0076 is less than alpha of 0.01. Okay. And then we just put this p-value in 0.0076. Okay. And again, the terms left-tailed and right-tailed might give them trouble. I used upper and lower tail test. It's the same thing, right? The lower tail test is the left tail, okay? In a certain survey, 516 people chose to respond to this question. Okay, so you're looking at a hypothesis test here, okay? The problem is that it's a voluntary response sample. People chose to respond. They're not randomly chosen. And so the problem here is that it's not a random sample. Okay? That's the key thing. Because it's a voluntary response sample. They weren't randomly chosen. They self-selected. You could think of it that way, right? And so if the p-value is low, the null must go. What it means is that when the p-value is very low, the null should be rejected. That's what it means to go, right? Okay. All right. In a certain survey, same sort of thing, right? Again, they're choosing to respond. Okay. So again, it's not a random sample. Okay. I think I'm doing this twice. Let me move on. Hold on. The alternative, the null should be rejected. Gotta read it carefully. And the last one, it was the first option, so. Oh, come on. Hold on. Oh, it is very low. The null should be rejected. So I'm just not reading it carefully. Yeah, okay. Another memory trick is that the p-value is high, the null will fly. So this is wrong, okay? Given that a hypothesis test never results in a conclusion, how is this memory trick misleading? First of all, if the p-value is high, that's evidence kind of in favor of the null, right? So it's definitely not A. The answer is actually D. It seems to suggest the null hypothesis has been proven or is supported, but this conclusion cannot be made. We never know if the null is true or not. Okay, the p-value means there's some evidence, but there's not enough evidence. So that's the key to take away from that. Okay. Common significance. So their answer is basically saying that If you chose a weird value for alpha, people might interpret that as meaning you were choosing it so that you could reject the null for your particular problem, right? So they want you to say this, that you're kind of jury rigging it, okay? In other words, if you had an alpha of 0.23%, like why would you choose that? And people would suspect you were doing it so that you could, reject the null, okay? All right. This is the same sort of problem, so I won't bother to go through it. It's the same sort of problem as what we did before. Same sort of thing, right? This is my test statistic. Again, you have to look at the alternative, right? This is the alternative, so it's a two-tailed test, right? The test statistic, again, it's always the z-score or the t-score, depending on the data that you're given, okay? The p-value is given. So all this is just really reading it right off, right? And what would you conclude? Okay, so the null is that it's equal to 0.91. Again, the equality always goes with the null. And you're obviously going to reject the null because the p-value is less than any reasonable value of alpha, right? So we know how to finish that off. Yes. So you have to be a little careful here. So you're testing the claim about inaccurate orders, okay? So here we're testing a manufacturer's claim. So we're saying the opposite. They claim that it's equal to 10%. So you're trying to prove that it's not equal to. Tests of manufacturer's claims are always the opposite. So they're claiming it's equal to 10%. So you're trying to test that claim. You're trying to prove the opposite. So it's going to be A. Let's just see if it goes any further in the problem. And the test statistic, again, I would just plug this into StatCrunch, right? I can run this. I know the number of orders. I know the parameter values. So we could go right into StatCrunch and we could do this. So here we would go to StatCrunch. We would go to proportion stats, one sample with summary. Number of successes. This is the expected number of successes, right? So I have to go back and read the problem carefully. So there's 33 orders that were not accurate among 392. So this is a number of successes, right? The numbers that were not. That were inaccurate. Okay, so 33 is the number of successes. 392 is the total number of observations. That's my sample size. I'm testing to see that it's not equal to 0.1, and I run my test, and there's everything I need. There's my p-value, my test statistic. I can see the p-value is way above. Alpha never goes above 10% in real life or even in the book. So the p-value is going to suggest that we're going to fail to reject. In other words, there's not enough evidence to prove that their claim is not true. All right, good. Same sort of problem, right? Now here you're going to be a little careful in clinical trials. So the real hard part of this problem is making sure you get the alternative right, okay? So it says, consider a drug that's used to prevent blood clots in certain patients. In clinical trials, we have a sample size here of 5,757 patients. 147 developed adverse reaction of nausea. We want to use an alpha of 1% to test the claim that 3% of the users develop nausea. So the claim is that the percentage is equal to 3%, okay? Notice, and this is important for the students to understand, there's no language suggesting it's greater than or less than. So we're testing the claim that it's equal. And of course, that's going to be not equal. That's going to be the alternative. So again, it's going to be A. Okay. Now you have to be a little careful because it says, does nausea appear to be a problematic adverse reaction? So there's a possibility it wants us to test to see if it's greater than 3%. So we have to be a little careful here. I'm going to say that the wording says it's not equal to. So sometimes you have to be careful. Sometimes the claim is that it's less than or equal to. And we want to test to see if it's greater than. So I'm going to change that. Okay. So this is where when you read the problem, you can change it a little bit based on your understanding. So a problematic adverse reaction would probably be when it's greater than 3%. Let's just see what they want. No. So here they want equals to, okay? So sometimes it can be a little ambiguous. In this case it is. Okay. So here my first interpretation was correct. All right. Why you would want to test to see if it's less than, because then it wouldn't be a problematic adverse reaction is a little beyond me. But nevertheless, sometimes you have to kind of play around. It's not so obvious. Again, I'm going to run this in StatCrunch, get my numbers. My test statistic will naturally come out of this. This will be my z-stat and my p-value and my decision, okay? But again, it's the wording, okay? So you want to tell the students to be careful. Based on this, I would say it's not equal to, sorry. But then when they say, does it appear to be a problematic adverse reaction? That could be a little ambiguous because problematic might mean it's greater than 3%. So again, they might have to play around a little bit, and it's natural. You can see that I ran into the same sort of problem, okay? Okay. Again, let's just try to get the alternative. Once we get that down, everything else is pretty straightforward. So in a study of 795 randomly selected medical malpractice lawsuits, it's found that 494 of them were either dropped or dismissed. Use a significance to claim to use an alpha of 1% to test the claim that most medical malpractice lawsuits are dropped or dismissed. Okay, so most would be greater than 50%. Okay, so we're trying to test. Again, this is not a manufacturer's claim. This is what we're trying to prove in a research setting, right? So it's going to be equals to and greater than. All right? So again, there's a difference between a manufacturer's claim and something you're trying to prove in research. And the reason why the last problem was problematic was it was a claim made by a manufacturer. So it could have gone both ways. Okay? So that's why you have to be careful. But here we're trying to prove something like in a research problem. So we're trying to prove, which is what the alternative is, that it's greater than 50%. Okay, good. And the rest of it's straightforward. Just put it in StatCrunch, blah, blah, blah. Okay. So getting the students to read and figure out the alternative is something that you might want to put on the board, some hints as to how to do that. So one of the things that you can do for the alternative, so one of the things that we always know for the null always has equals in it. Okay? So for the alternative, it's what you're trying to prove. And usually you have two sorts of situations. You're either trying to prove a research question in which the alternative is the way it's stated in the problem. If you're testing a manufacturer or a business claim, when you have a research claim, the alternative is the way it's stated in the problem. So it's the stated claim in the problem. When you're looking at a manufacturer or a business claim, a claim made by a business, it's the opposite. So notice that in the order problem with the incorrect orders, the claim was that pi is equal to 10%. And we were trying to prove that it's not equal to 10%. Okay? So this will help the students. Okay, so let's go ahead and read this. So notice that, again, we don't have a manufacturer. We're testing a research claim. So we're testing the claim that 26% will be yellow. Okay, so here the alternative will be not equal to. Okay. And again, this is a little, and you really do have to puzzle through this, because we just got through saying that when you're not testing a manufacturer's claim, it's the opposite of the claim and the problem. But notice here, the claim is, the research claim, we're testing the claim that under certain circumstances 26% will be yellow. Well, equals always goes with a null. And since there's no language suggesting it's greater than or less than, we're going to have to choose not equal to. I don't like this book for hypothesis tests, because the claims, it's not obvious a lot of times if it's the null hypothesis or the alternative. They mix them. So here, the claim is actually the alternative, the null, which is stupid, because the claim is what you're trying to test. It should be the alternative. So this is kind of jacked up. So you have to read the problem carefully. Okay. And again, the rest is all the same, right? Consider a sample of 45 football games. 32 of them are won by the home team. We want to test the claim that the probability the home team wins is greater than 1/2. So what we're trying to prove is that it's greater than 1/2. So that's clearly going to be our alternative. Okay. Generally, and there are times when the students might get it wrong, but what they should be able to do is they should be able to get it right the second time. Okay? Because the problem is always the alternative. And, it can be, like you saw that one I missed myself. It can be ambiguous. But they should definitely get it the second time, okay? So on the exam, I'll give them at least 2 chances on the problem. Okay. Type 1 and type 2 errors, okay? So we have to think a little about the hypotheses, okay? The percentage of household pets with more than one pet is equal to 65%. Okay, so this is the null, okay? So a type 1 error, if we think about the different ways that we can make an error, okay? So this is our decision, and this is reality. So this is when the null is actually true, and this is when the alternative is actually true. And this is when we decide that we fail to reject the null. And this is when we decide to reject the null. Okay? So when the null is true and we fail to reject the null, we're okay. When, however, we fail to reject the null, in other words, we go with a null and the alternative is true, this is called a type 2 error. This is sometimes called misdetection. In other words, something actually happened, but we decided nothing happened, okay? A type 1 error is when we reject the null. We say something happened and nothing happened. Sometimes people call it a false positive. Okay? Oh, sorry. My pen changed color spontaneously. Okay. So this is a type 1 error. This is called a false alarm. You reject the null, but you shouldn't have. So this is what's going on here. So in this case, they're claiming that pi is, 65%. Okay. This is the null. The alternative is going to be the opposite. Pi is not equal to 65%. So here we're going to conclude that the pi was not 65% when it actually was. That's what's going on here, okay? So we're going to reject the null, okay, when the actual percentage is different than 65%. Okay, hold on. Let me go back and make sure I did this right. Hold on. The null is true, and we reject the null. So I need to go back and change that, right? So the null is actually true. So we reject the null, but the null is actually true. Okay. So drawing that little picture out helps the students a lot, that little table, okay? Okay. An experiment tests whether dogs can detect cancer by sniffing 7 urine vials, one of which has results from a cancer patient. Okay. And so the probability that the dog will randomly guess the right one is 1 in 7, right? So we want to test to see if it's not 1 in 7. Okay. So what would the decision be for a significance level of 9%? Okay, so let's think about this. When alpha is 9%, hold on. Oh, I'm sorry. A p-value of 5% is obtained. If our significance level was 9%, which it shouldn't be, we would fail to reject, right? So the null hypothesis would not be rejected. And our conclusion, therefore, would be that the dog randomly guessed. If we don't reject the null is that they randomly guess. Okay. Hold on. I'm sorry, the p-value is less than, so the null hypothesis will be rejected. The p-value is less than alpha, sorry. And we would guess that it's better than just random guessing, right? So it wouldn't randomly guess. It would be able to actually detect it. Yeah. So you gotta be careful with the language. Okay. So if the decision in part A is an error, so in other words, we reject the null hypothesis, but we shouldn't have, okay, what is that? Well, let's go back and look at our table. So we rejected the null hypothesis, right, but we shouldn't have. That's a type 1 error, okay? So it's a type 1 error, okay? So the p-value, so it's one of these two. The p-value would cause rejected hypothesis, and the reality is that they actually do guess randomly. So we reject the null, but we shouldn't have. Okay? Okay. And the last one. So drawing that table hopefully will, oops, I hit similar, I didn't hit next one, sorry. Okay, consider the test a defendant is not guilty against a defendant is guilty. And hopefully this is pretty straightforward, right? A type 1 error, think about what it is. The null is not, the null is true, but you reject it, right? So in other words, the person is not guilty, but you say that they're guilty. Okay? So let's see. Rejecting H0 implies that the null hypothesis, the defendant is not guilty, is false, and that's what's going on here. Okay? And again, this chart will help you. Type 1 is when the null is actually true, they're not guilty, but you reject the null and you decide that they are. Okay? And of course, the type 2 would be the opposite. Okay? So the consequences is that an innocent person is being jailed, right? So an innocent person's being convicted. Okay. So that's just putting it into everyday terms, right? Okay, and let's see. Explain in context the conclusion of the test if you fail to reject the null. So if you fail to reject the null, you're saying there's not enough evidence, right, to make you believe the alternative. So if we fail to reject the null, implies that the null hypothesis is a possibility. Therefore, the defendant's acquitted and set free. Okay. You don't say absolutely true. We never know if a person's innocent or not. A jury never says they're innocent. They just say they're found not guilty. There's not enough evidence to find that they are guilty, right? Right. And that should pretty much do it. So I hope that helped. If you have any questions, feel free to let me know, okay? All right, thanks.